Now, lesson 4, a little continuation from lesson 3 where we talked about efficiency, we're going to start talking about the limits of certain algorithms. So to start us off, let's get a little prompt here. So this is kind of a recap. What's the difference between a reasonable and an unreasonable time algorithm? Well, if you remember from yesterday or from lesson 3, we did the raffle tickets and kind of, do we pair up? Do we do a group? Well, here's what it comes down to. A reasonable algorithm grows at a polynomial rate or slower. So let's remember this graphically. A quadratic. This is a polynomial like x squared. Could be a linear. This is kind of the normal raffle. And this is y equals x. And the last one is more of a logarithmic one, which is also reasonable. So y is equal to the square root of x. So visually, that is what we would see for a reasonable algorithm. The unreasonable algorithm grows exponentially. And that would be this graph right here, where the group raffle, there were so many checks to do. So this grows at a y equals 2 to the n, where n is the exponent where that one changes. So graphically, this is the best way to remember unreasonable versus reasonable. So the key is this. The time to solve an unreasonable algorithm grows rather quickly, even for relatively small problem sizes. So that's where that all comes into play. All right, so let's look at the next little thing. Here's our activity we did. We did the traveling salesman. Now, here's what the traveling salesman problem brings up. Prompt, how many different paths can you find to visit all your friends' houses? The rules are you must start and end at your own house, and you can only visit each house once. So knowing that, if we were to go ahead and just to look at the first sample, we're starting at house 1. Well, which direction do we want to start? Well, let's go to the right. So I'm going to go from house 1 to 4. And then from here, I can choose either 2 or 3. So let's go ahead and just go up to house 2. Now, there's only one more house to check, which is 3. And now we can come all the way back to the starting. So this is the path we chose to take. Let's go to the right, come up diagonally, go to the right to number 3, come back diagonally till we're back home. So let's go to the next one. Here's some different representations of this. Now, this is the one we just did right here, but there are actually more available. And so here are a few different paths. Now, the key to this, though, is the following. What do you need to know if you're going to determine the best path? That is, if we're going to follow one of these paths, which one would be deemed best? Well, common sense would say the following. We see the different paths here, but what these do is show the total distance. So out of these 3, we can see that this one would be the more efficient, because efficiency comes down to which one has the shortest distance. And so that's what this is all about. So let's go to this next thing here. What the prompt shows, look at, what if we have all these different places to visit? How would we determine the best path? Well, kind of as we go along and investigate amongst the students, most would come up with the simple solution that, well, look at, if we're starting here, then let's just go to the next closest. So by bird's eyeing it, that might be this one. Now, where do we go from here? Well, we got to visit each house. So logic might say, let's go to this house. Let's go to this house. And we got a couple houses here, so it's either go this way to this house or come down here and come up, but we have a lot of choices here, because what we would realize is there might be one more efficient way if we really delegated and looked at all the different arrows or short little paths that we did and measured them up. So let's go to this next thing. This is known as the traveling salesman problem. For every new place to visit, the number of positions for possible paths will increase factorially, okay? So let's go to this little chart. So we can see this, obviously. If we have one house, that's one path, okay, to itself. If we have 2 houses, we have two total paths. Might sound strange because we think, well, there's only two houses, there's one path, but we'll take a look at that in a second. And then if we have three houses, we have six paths. So let's kind of break this down and take a look, and then we'll talk about this factorially. So on here, here's the two-house scenario. Well, what we would look at is the following. If I go from my starting place to the house, remember we have to come back. So that is why it says there's two total steps. Here's the three scenario. We start from the green, we choose, let's go this way. From here, we go up to this house. From here, we go back to the start. Now, that's three paths. Well, just remember, the other option is going to be, let's go start here, go this way initially, and come back. So that is why with three houses, there's actually six different steps to find all the paths. All right, so let's go and look at this sample. Here was the fourth one. So if we just kind of let this animate, we'll see we'll start in this upper left corner one here, and let's go ahead and advance it. So this one, if we start going to the right, it chooses the path to just go along in a circular orbit. Let's go down to this one. This one we're going to start up. And so you can see we're kind of going counterclockwise in the first one, but we go clockwise in this one. Now let's go back up to this one. Now this is going to be similar to the first, as we're going to start to go to the right. But as you can see, this kind of reminds you of the sample we did a couple slides ago, where we chose from here. Once we get to this one, we already went up this way in this example. So the only other option is to go this way and then come back around. Likewise, let's look at this bottom option. This is very similar to the first one. So you can see the paths. Now, with the first four here, it was either let's start to the right or let's go up. So what we're left here is to do the diagonal approaches. So we'll start up to the right. And once we did this first one, we said, look, let's just come back to the left here, come back and back over. So this one, we got to go up, come down. And it shows that indeed, with all these different scenarios, there's a total of 24 steps involved. So if we go to what's called factorially, this is what factorial is. Since we have four houses, we can write this as 4 factorial. But mathematically, it's 4 times 3 times 2 times 1. And that gives us 12 times 2, which is 24. All right, so let's go to the next thing here. Here's what factorial actually means. So this is the breakdown. I'll advance it quickly. So you can see if it's 5 houses, then that's going to be 5 times 4 times 3 times 2 times 1. Well, that's going to give us 120. So this is starting to grow exponentially. Look at 10 houses. Look at the number of steps we need to do. 3,628,800 steps. That is a lot. So as you add another house, the number of steps grow exponentially. In this example, it's the factorially. All right, so here's what we looked at, problems. Remember now, any task that may or may not be solved with an algorithm is a problem, all right? Sorting a list is a problem. We looked at that a couple sections ago. And if I said, let's just sort the list 2, 3, 1, and 7, this is called an instance of that problem. It's a sorting problem, but just a smaller instance of it. Now, a couple other things that go with problems. Here's a decision problem. It's a maze. So the question is, well, is there a path that exists? The trick to this one would be, finding a algorithm that allows us to easily check all the different paths. And there's not a nice little looping algorithm that would probably allow us to do this. So this becomes one of those problems that has many, many and very difficult solutions. The other one was optimization problems. Okay, so that's really what we've been doing. What's the shortest path? So how can we optimize? That's the difference. Okay, so both of these are very unreasonable. So let's go to this optimization. This is the traveling salesman problem. It can be solved with an algorithm which checks each possible option, but it will take massive amounts of computing power to compare every single option, especially as the number of homes that we want to visit increases, like we saw in the last couple of samples. Therefore, it would take an unreasonable amount of time for the solution to be calculated for most instances of the problem. All right, so that's where we introduce heuristics. Heuristics provide a good enough solution to a problem when an actual solution is impractical or impossible. So that means we'll come up with some sort of solution, some sort of algorithm that's good enough. Maybe not the best, most efficient, but good enough for our tastes. Okay, so here's what we did in class. You can see that there's an activity in level 2 of lesson 4. So let's jump over there. And what this is designed to do is for you to kind of play around with using that heuristic approach, choosing the best path. So when I run this, here's one thing that this program does. We're starting in the green. So when you point to different dots, it will show you the distance from the green to that dot. Now, as we look at this, you can see that this one represents the shortest distance. So if we follow our algorithm that we designed before, which is, hey, let's just go to the next closest one. When we click on this, it puts it together and shows here's the total distance. Now, from here, I have 83, distance of 83, and I have a distance of 78. Now, following our rule, we could certainly go in this route, okay? And what would happen is we would keep clicking because we got to come back to the beginning where we have 1,336 as a total distance. Now, let's reset it and let's go in this direction. Start from here. And right now, I'm kind of bird's eyeing the distance and saying, hey, this could be good enough. Well, look at that. That's a little bit less than that first one. So heuristic is all about, hey, can we come up with a decent algorithm that is good enough for us to use as a solution? Now, let's go to the step 4, and I'll just jump back here. So step 4, in lesson 4, level 3 in lesson 4, has us do a couple things. We'll try our heuristic approach, which is the closest one, but then we'll also try what's called the brute force. That means just clicking on different dots to see if anything becomes better. So let's go back here and let's jump over to section 3. All right, so here's what we're looking at. This one's a little different because it randomly will pick different ones when you say a new level. So going in our heuristic approach here, we're starting in the green. Let's go to this one, then probably this. And as I click here, I'm kind of using the eyeball approach. I have a distance of 1,044. Now, I'm going to reset this one. And let's do a brute force. So let's just go ahead and start clicking. And obviously, I'm not being very efficient with these. And I have a much bigger distance. So our heuristic approach, which was, hey, let's kind of follow the closest one, should work. Now, let me go to a new level. So here's the thing that you got to remember when we're talking algorithms. If this was a computer trying to solve this, a computer does not see these dots like we do as human beings. It would literally, if we're starting at the green, it would have to see the distance from this green one that each one occupies From that, it could make a decision to move to the next possible location. For us as a human, we can bird's eye and say, look, I can see that these two here are definitely closest, so let's draw a line. Now, from here, yeah, this looks closest, and it's almost common sense. So our heuristic approach is probably going to end up with the shortest distance. But you have to remember, a computer cannot see those dots like we do. So a more intricate algorithm would need to be designed. All right, so let's go back here and let's take a look. How did you create your heuristic? Did you change your heuristic after testing it out? Well, yes and no. We really said, look at, if we follow the closest, the one that's closest and start connecting, on average that will work, but sometimes the one that's closest ends up giving us the a longer route. So we have to use a little bit of good enough guessing in a few instances, but we can eyeball it as human beings. All right, so we explained the heuristic. Let's try to pick the one that's the next closest, and we'll start connecting. All right, so this is a perfect example. At each node, travel to the next closest node. And this one takes this method where, let me go ahead and get a pointer going here. All right, which is say, hey, let's follow this path right here. 4 to 5, 5 to 6. Now, when you got to this one, we probably could have went this route. Because I think if we would have did this route, we probably would have saved a little bit, because this distance here going around, this is a shorter distance from this last one to here than this last one is to this red dot, simply how it's laid out. So there are little things that we can modify as we go along. So here are the takeaways. The traveling salesman problem is called an optimization problem because we're trying to optimize or find the best path. It is also unreasonable because there's not a nice algorithm that can solve the problem in a reasonable amount of time. There's a lot of looking and guessing and number distance figuring out that we may have to do. So we need to use a heuristic to come up with a solution. That is something that's good enough for most instances of the problem. So that's kind of the essence of what heuristic is. So when we go back to the ones that we just talked about, so this one here, this would be a really tricky one, because the whole point of a maze is you start in one spot and then you have to make a decision. Well, can I go forward? Well, if not, let's turn. Now, can I go forward from here? So it's a much more complex. And then if you hit a wall and you can't go any further, you kind of have to go backwards. And for a computer, that really becomes a difficult task. All right, so a couple takeaways here. There are some problems we've proven that no computer will ever be able to solve, okay? And the halting problem is a very famous example, and in general, we can call these problems undecidable. Now, don't worry about the halting problem. It follows a video, and we won't have to worry about it for this one. But we just want to know in this lesson, it's all about the heuristics, finding a good enough solution. Okay, so why is a heuristic acceptable when it doesn't always produce the best result? Because it's close to being probably one of the best results. And that's what it's all about. All right, so heuristic provides a good enough solution to a problem when an actual solution is impractical or impossible. An undecidable program or problem, a problem which has no algorithm that can be constructive, that is always capable of providing the correct yes and no answer. And those examples that we saw in this lesson are exactly that. They make it very undecidable if a perfect solution can be found. All right, now what you can do is inside back into your code.org, go ahead and fill in the questions for steps 4 and steps 5. Which are check your understanding, a couple simple ones, and go ahead and do that.